This material is made available to you by or on behalf of the University of Melbourne under Section 113P of the Copyright Act 1968. It may be subject to copyright. For more information, visit the University Copyright website.
All right. Okay, let's start lecture 9. So, yesterday we were looking at a uniform flow, a source, and a sink. Right, and we were deriving the equation of the separatrix. Okay, so you all should know that this term, tangent theta A minus theta B, is equal to 2ys divided by x squared plus y squared minus s squared. Okay, and we know this relationship because we have derived it earlier when we derived the stream function of a source and a sink. Okay, and if we did not know that, we can derive it ourselves, all right, using the differential rule, right, when you expand this term here. Sorry, difference theorem. Right, expand this term. Okay, so the next thing that I'm going to do is I'm going to bring these terms to the left-hand side and my tangent term here to the right-hand side. And I end up with the equation of my separatrix, which is x squared minus s squared plus y squared equals to 2ys cotangent, right, which is 1 over tangent, 2 pi u infinity y over q. Right? Right, so this equation here is our separatrix, right? So it's separatrix. Okay, and it has a shape of an oval. And we call it the full Rankine body. Right, so if you have a look at this flow, we have a uniform flow from right to left. We have our source at the right-hand side of our origin and a sink on the left-hand side of the origin. Okay, and you should be able to tell me the location of our stagnation points. Okay, which we know is located along the x-axis, so y is equals to 0, and it's at plus minus s square root of 1 plus q divided by u infinity pi s. Okay, and this point here is just negative of that. Right, and this equation, this separatrix here is just our equation for a half Rankine body. which we have derived earlier on. Oh, I can't do that. Okay, and you should be able also to draw the streamlines and the direction of the streamlines as well. Okay, and I hope all of you know that in this region here, which is close to the stagnation point, okay, if I zoom into that region there, oops, you must know that there are going to be two streamlines going out of the stagnation point and 2 points going into the stagnation point. Okay, so here's my source, right? So I'm definitely going to have one streamline going into the stagnation point. Right, on the right hand side here is my free stream or my uniform flow. So that has to be going inside my, or approaching my stagnation point, right? And therefore, these two streamlines are pointing outwards of my stagnation point. Okay, everyone understand? Yep. Any questions? No? Yep. Okay. Let's move on then. So, what we have is a flow over a Rankine body. Okay. And we can again, if I replace my separatrix with a solid body, okay, we can then have a flow over a full Rankine body. Okay. And the flow looks, I guess, something like this. Right? So that's a flow over a full Rankine body. Now, if we have a reverse flow direction, all right, if our uniform flow is moving from left to right, you're going to have a very different flow pattern. Okay, so a flow pattern will look like this. Okay, and this flow field, all right, depends on the parameter U infinity S over Q. Okay, and I want you to do this at home during the weekend to show that when this parameter U infinity S over Q is less than 1 over pi, you're going to have stagnation points along the y-axis. So you're going to have two stagnation points here. Okay, and as I increase U infinity S over Q, right, hopefully you can see that the flow field changes and I get only one stagnation point at the origin, okay, when U infinity S over Q is equals to 1 over pi. Right, and now when I increase U infinity S over Q further, now my stagnation points are going to be occurring along the x-axis, okay, here and here. Right, so this shape, this full Rankine body is, I guess, somewhat useful. It's a semi-streamlined body. Okay, but we are still not addressing issue number 2, which is we are not able to apply an angle of attack to this full Rankine body. So when I change my direction of my uniform flow, right? You can see that our full Rankine body actually breaks down. We don't get a full Rankine body anymore. Right? So what happens if I move my source and sink closer to each other? All right? If I move both of them towards the origin. So according from our equation of our separatrix, as s approaches 0, okay, you're going to get a circle, all right, x squared plus y squared, which is a circle, which has a radius of 0. Right? Okay, and I guess that's not very useful, right? Then you just end up with a uniform flow. Right? So basically, your source and sink just cancels off each other. Now, what if we set the strength of Q to be equal to a constant K divided by S? So basically, as S approaches 0, right, your Q increases and approaches infinity. Okay, such that Q multiplied by S gives you a constant K. So if we do that, now we know that this S terms goes to 0, right? But this cotangent term goes to infinity, right? And what we have actually is this right-hand side here being a constant, right? Or tending to a constant. So x squared plus y squared now approaches a constant. Okay, which means that our separatrix is going to be a circle. Okay. Now let's just consider a flow where we have a source and a sink, and a source and a sink approaches the center or the origin. Okay, and this is known as a doublet. Let's ignore our uniform flow at the moment. Right, so the stream function for this flow is going to be Q over 2 pi theta A minus theta B, and theta A minus theta B can be replaced with a constant which I've just called alpha. Okay, and alpha is this angle here. Okay. So let's try and derive this doublet. So I've labeled this diagram a little bit. Okay, so I have LB, oops. Okay, which is the distance from here to here. Okay, perpendicular to this line, and LA to be this line here, which is perpendicular to this line here, and also, sorry, perpendicular to this line. Now, as S approaches 0, okay, our angle alpha is going to become small, right? And, oh, well, let's just do this together. Okay, so I'm just going to rewrite it again. Oops. Okay, so we have our stream function psi to be equal to Q over 2 pi theta A minus theta B. Okay, and that's going to be equal to Q 2 pi alpha, which you can't see. Right, and as I was mentioning before, we want to express alpha in terms of theta. Oops. Okay, and theta is just the angle which is made between the horizontal and some point xy, right? Starting from the origin here. Okay. Now we are considering what happens when s approaches 0, right? So as s approaches 0, okay, as our source and sink approaches the origin, what's alpha going to tend to? It's going to be 0, right? So this one here is going to approach 0. Okay? Right, and therefore, we can say that theta A is going to be equals to, or well, it's going to be approximately equal to theta B, which is approximately equal to theta. Right, everyone follow? Yep, so basically, these three lines here, okay, are going to be parallel to each other. Okay, these three lines are all parallel to each other as s approaches 0. Okay, now I'm going to consider this region here. Okay, and I've drawn it here. Okay, so if I consider this region here, I'm going to get something that looks like this. Okay, and this angle here is theta, right? Because theta A is equals to theta B equals to theta. So this is, I'm just going to call this theta. And I know that sine theta is going to be LB over S, right? Okay, so therefore, sorry, LB. Okay, so therefore LB is just going to be equal to S sine theta. Okay, just bear with me for a moment. You'll see why this is important later on. Right, and this region here, all right, is also another triangle, which I've drawn as such. Okay, and sine theta here is going to be equal to LA over S. Oops. Sine theta is going to be equal to LA over S, okay, where basically LA is going to be S sine theta. Okay, now for small angles of alpha, what can we say about sine alpha? Sine alpha is approximately equal to what? Alpha, very good. Okay, so for small angles, sine alpha is approximately equal to alpha. Okay, and if you go back to our diagram here, okay, this is alpha here. Okay, so sine alpha is going to be just this length here, which is LA plus LB, divided by this length here, which is going to be R. Alright, because for very, very small angles, this length here is going to be equal to this length here, which is going to be equal to this length here, as the lines are all parallel. So it's going to be divided by R. Okay, so I'm going to get LA plus LB divided by R. Okay, and we know what LA and LB are because we found them before. So it's just going to be 2s sine alpha over R. Okay, so we managed to express alpha in terms of theta. Right, so I want to substitute this expression here back into my stream function. Okay, so remember my stream function is psi equals to q over 2 pi alpha. So now it's just going to be q over 2 pi 2s sine, oops, not alpha but theta over R. Okay, and I can take this away. Right, and remember I told you that we want to have Q multiplied by S equals to a constant. So I can rewrite it as K sine theta over pi R. Okay. Right, so this is your stream function in cylindrical coordinates, and I can rewrite it in Cartesian coordinates as well. So I'm going to get, oops. I'm going to get equals to K. Now, sine theta is just going to be equal to, what sine theta equals to? It's going to be y over R, right? So if you guys can't remember, so remember that sine theta is equals to y over r, okay, and r squared equals to x squared plus y squared. Okay. So sine theta is equals to y over r, so I have a y here. Okay, and r squared is just x squared plus y squared. So I'm going to get ky over pi x squared plus y squared. Okay, and that is going to be equal to some constant, right? Some constant c, which I'm just going to call that. Okay, everyone following so far? Yep. Okay, so we have our stream function. So we want to know how the streamlines look. Okay, so all I have to do is then rearrange my stream function here, right? So we know that this is equals a constant for a streamline, okay? And I'm just going to take this term to the right hand side and C to the left hand side. Okay, so I'm going to get x squared plus y squared equals to ky over c pi. Okay, and again, I'm going to use completing the square. So I'm going to get x squared plus y minus k over 2c pi squared equal to k over 2c pi squared. Okay, and this is an equation of a, what is it? Circle, right? Which is centered at x is 0, y is k over 2c pi. Very good. So it's just a circle. With radius k over 2c pi. Okay, and it's located at 0. This is going to be k over 2c pi. Okay, very good. Right, so if I do draw the streamlines out, it's going to look something like this. Okay, so this height here is going to be what should I do? No, let me do this. Right, so this point here is going to be 0 k over 2c pi, right? And hopefully you can see that the radius of this circle r is also k over 2c pi. Okay, and we call this a doublet. Okay, so I hope you all notice that all these streamlines, all of the streamlines, it crosses through the origin. Okay? And all of the streamlines. Okay. So for different streamlines, for different values of C, okay, you should be able to show that no matter what constant you're using, it always crosses through the origin. Okay? Any questions? Yep. Okay, so this flow field is known as a doublet, all right? So when you have a sink and a source which is placed on top of each other, you get a doublet. Right, and we can then add a uniform flow, all right, from right to left. Okay, and we have something which looks like a flow over a cylinder, right, or a flow over a cylinder. Okay, and we'll prove that very shortly. Now, it's very important that your doublet, all right, your doublet here, the top bit is moving in the anti-clockwise direction, okay, and at the bottom here, it's moving in the clockwise. Your streamlines are in the clockwise direction, okay. So please pay attention to that, okay. Now, if I have negative, all right, if my doublet is negative, right, I'm going to get the opposite flow, where now at the top here, my streamlines are moving in the clockwise direction, and at the bottom here, I have my streamlines moving in the anti-clockwise direction, okay? And when I have a flow, a uniform flow, right, which is moving from right to left, I'm going to get very, very different flow features, okay? You can see that all the streamlines get sucked into the origin instead of getting a flow over a cylinder. Okay, so you must know, or you must be careful, I guess, with your signs, right, when dealing with doublets. Okay, right, so back to our usual, all right, the first step is always to write our stream function, okay, for a doublet and a uniform flow. Right, that's always, remember, step number 1. Oops. Right, and I'm going to write it in Cartesian coordinates for now. So psi is going to be equal to negative u infinity y, okay, plus ky over pi x squared plus y squared. Okay, so that's always our first step. The second step is then to find our velocities, u and v. So u is just going to be del psi over del y. Okay, and that's just going to be equal to negative u infinity plus k x squared minus y squared divided by pi x squared plus y squared, everything squared. Okay, and I'm going to call this equation 1. Okay, and next I want to calculate my velocity v, or I want to have an expression for velocity v. So v is just going to be negative del psi del x, and it's just going to be 2kxy over pi x squared plus y squared. Right, you all know how to differentiate this term with respect to x and y? Yep, good. So, once we know our velocities, we can then find our stagnation points as usual, right? So, hopefully you can see that from equation 2, okay, we can see that v is going to be 0, okay, when either x or y is going to be 0. And I'm going to substitute y equals to 0 into equation 1. Okay, so if I substitute y equals to 0 into equation 1, I'm going to get 0 equals to negative u infinity plus k over pi x squared. Therefore, if I rearrange it, I should be able to find x, which is going to be plus minus k over u infinity pi. Okay, and therefore my stagnation point is at plus minus k over u infinity pi 0. Okay, is everyone following so far? Now, I'm expecting a question here. Why did I substitute y equals to 0 instead of x equals to 0? So if you substitute x equals to 0, right, you will not get a real solution, right? That's the answer. Okay, so okay, which means that there is no real solution. Okay, that's why we had to substitute y equals to 0. Right? If you don't believe me, you can try and do it, and you'll find that there isn't any real solution. Okay, so stagnation points, what's the next step? Separatrix, very good. Okay, so you know our stagnation points. I'm going to substitute my stagnation points back into my stream function. Okay, so psi, oops, sorry. Okay, so I'm going to sub stagnation point into my stream function. So I'm going to get psi equals to negative u infinity 0 plus k, my y0 divided by blah blah blah. Okay, and I know that my stream function constant is going to be equal to 0. Okay, so next is I'm going to take this constant, substitute back into my stream function to get the equation of my separatrix. Right, so therefore, okay, so therefore 0 is going to be equal to negative u infinity y plus ky divided by pi x squared plus y squared. Okay, and you can see that we're going to have two equations of the separatrix. What's the first one? Y equals to 0. Very good. So one of the separatrix is y equals to 0, right? Which is just my horizontal axis. Okay, And the other one, we have to do a bit of a rearranging. Okay, so what I'm going to do is I'm going to take this term here, move it to the left-hand side. Sorry, move this term to the left-hand side and then move this to the left-hand side and then move this back under. Well, you'll see what I'm doing. You'll end up with x squared plus y squared. Okay, u infinity goes underneath here, so you get k over pi u infinity. Okay, and this is an equation of a circle centered at 0, 0 at our origin. Okay, so separatrix is a circle. Okay, and our radius of our circle is going to be square root of that term on the right hand side there, right? So the radius of this circle I'm just going to call A, and it's going to be equal to square root of k over pi u infinity. Right? So very quickly, I'll just oops. So. Okay, so we get a separatrix, which is a circle with radius square root of k over pi u infinity. Right, so remember I have stagnation points, plus minus square root of k pi u infinity, right, and this circle is my separatrix. Okay, and don't forget I have another separatrix which goes along my x-axis. Okay, so I can replace my separatrix with a solid boundary, right, and then what I get is a flow over a cylinder. Okay, I can also replace my other separatrix, the horizontal line, with a boundary, solid boundary, and now I get to model a flow over a bump. Okay, right. Now we can also express our stream function in terms of u infinity, x and y. Right, so I'm going back here. Okay, so what I'm going to do is I'm going to substitute k over pi to be equals to a squared u infinity into our stream function, right? And basically this is just rearranging this here, okay? I'm just rearranging that. So what I'm going to get now is my stream function, which looks like that. So negative u infinity y plus a squared u infinity y divided by x squared plus y squared. Okay, now I want to convert this into cylindrical coordinates. Okay, and I'm skipping a few steps here, but you should be able to show that psi is just going to be equals to u infinity sine theta a squared over r minus r. Okay, and you can very easily do this because you know that y is just equals to r sine theta, and you know that r squared is equals to x squared plus y squared. Right? So using this information here, you can very easily convert from Cartesian to cylindrical coordinates, which is what I've done. Okay, and we want to deal in cylindrical coordinates because getting the velocity is actually much easier. So if I want to find ur, my radial velocity, it's just going to be 1 over r del psi over del theta, which we have shown earlier. Right? You know how to prove this. Okay, and that's just going to be equal to u infinity cosine theta a squared over r squared minus 1. Okay, and u theta, oops. Okay, our azimuthal velocity is just negative del psi over del r. And that's just going to give us u infinity sine theta a squared over r squared plus 1. Okay? Is everyone following so far? Any part you want me to repeat? All good? Yep. Okay, so this is my velocities, right? My radial and azimuthal velocities everywhere in my domain. Okay? But if I just want to know the velocity on the surface of my cylinder, okay, which is also my separatrix. All I have to do then is to replace r with what? Yep, radius. So r is going to be the radius of my cylinder. Okay, so r is then just going to be at A, which is on the surface of my cylinder. So then, very nicely, you should be able to see that ur is going to be equal to, so this is going to be 1 minus 1 is 0, so ur is going to be 0. And u theta is just equals to 2 u infinity sine theta. Okay? Should see from here it's just 2 u infinity sine theta. Okay, and why is the velocity important? Why is the velocity on the surface important? What can we find using Bernoulli's equation? Pressure, right? So now we can use Bernoulli's to find pressure. Very good. Okay, so we got our velocities. We can use our Bernoulli's equation so we can find out what's the pressure acting on that surface. All right, so using Bernoulli's, I get an expression for the static and dynamic pressure. Okay, and I can then express my velocities in terms of pressure difference, PC minus P infinity. So P infinity is just my free stream pressure, and PC is the pressure on the cylinder. Okay, and we want to find the pressure coefficient, right, which is PC minus P infinity divided by half rho U infinity squared. Right, I know what PC minus P infinity is as a function of velocities, okay, from a Bernoulli's equation, so I can substitute that in. and I end up with Cp being 1 minus uc minus u infinities, both squared, right? So uc is the velocity magnitude on the surface of my cylinder, which I know is just square root of ur squared plus u theta squared, right? Yep, and ur is equal to 0, so uc actually is just u infinity, sorry, u theta, right? Because this just goes to 0. Okay, so substituting that back into my expression for Cp, I end up Cp just as a function of theta, right? 1 minus 4 sine squared theta. Okay, and this is the pressure distribution around a cylinder for a two-dimensional, inviscid, incompressible flow. Okay, so if I use MATLAB, I can plot Cp against theta, right? And you can see that the profile is symmetric, right? It's periodic. Right? Now, if I plot the Cp graphically, all right, you can see that it is symmetric, front and back, top and bottom. Okay. And this is the velocity profile around the cylinder. Right? As you can see, when there's high velocity, you're going to have low values of Cp. Okay. And when you have low velocities, you're going to have high values of Cp. Right? And remember, vectors pointing inside of the solid body is positive values of Cp, pressure coefficient. Okay, and this, I guess, this pressure coefficient is of an ideal flow, right? So, which one is it? It's this one. Okay, so we have no flow separation. Okay, you can see that the streamlines depart and then join back together. Right, and that is for an ideal flow. And what I've showed you just now was an example of a creeping flow. So basically the Reynolds number is very, very, very low. But in real life, in most engineering applications, our Reynolds number is quite large. Okay, and you can see that the pressure distribution is not symmetric, right? And that's because of flow separation, right? So it would look something like that. Right, there's going to be vortical shading at the back of the cylinder. Okay, but this is something which we cannot simulate due to the limitations of our inviscid approximation. Okay. Right, so that's all for today's lecture. Next week we'll learn something new. All right, so we have learned this term called psi, which is our stream function. Okay. But next week, we're going to learn its sibling, right? Velocity potential, phi. Okay. So please read your lecture notes in advance, and we'll go through them on Monday. Thanks.